Hi, everyone. Welcome to the SpellML product demo. I'm one of the moderators here. I work at Spell with Circon. I'm here to introduce Circon, and then we'll kick off the demo. So it's my pleasure to introduce Circon Piantino. We've been working together for the past couple of years, and he's an entrepreneur and leader in technology business based in New York City. Currently, he's the founder and CEO of Spell, and previously he was the founder and site director of Facebook New York. And most relevant to this conversation, Circon co-founded Facebook's AI research lab with Jan LeCun. As well, during his 9 years at Facebook, he also designed and led the development of many Facebook products that I'm sure you're all very familiar with, including the infrastructure for the newsfeed, EdgeRank, Timeline, and Messenger. Circon is also an active advocate for technology industry in the city. He's previously served on Mayor Bloomberg's Council on Technology and Innovation, and currently on the board of Tech NYC and AFSE. And Circon holds a BS in computer science from Carnegie Mellon University. Okay, Circon, I'll let you kick it off from here.
All right.
The floor is yours.
Thank you, Sydney. We have a couple things that we're going to do today. I have a couple slides that I want to run through, just talking about Spell, what we are from a high level, what we provide, and some of the reasons that we started the company. Then I'm going to do a product demo, and then as people are trickling in and out, I know this is a 90-minute session. We're actually going to go back to the beginning and do it all over again. So if you stick around, you'll get to see Spell twice, and if you're just joining us, I hope you enjoy the demo. Let me share my screen. Let's get started. So we are MLOps for deep learning. Just a quick reminder, I think Sydney covered a lot of this, but I spent about most of my career at Facebook. I built the newsfeed systems and designed all our ranking algorithms. Moved to New York, founded the Facebook office here, and we grew that to about 1,500 people, and then co-founded Facebook AI Research with Jan LeCun, where we developed not only worked with some of the smartest people in the AI research space and grew that team to about 100, but also designed our first infrastructure tools, our first GPU clusters, sort of all the machinery behind our AI research systems. And that was where a lot of the inspiration for Spell came from, and I'll talk about that now. First, just starting with our mission, make AI easier and more accessible. Pretty straightforward. I think a lot of what's difficult about AI right now is that there's a lot of infrastructure and tooling that is lacking when you're doing things with deep learning particularly. And so that's what Spell is founded to solve. I kind of think about this as two sort of main challenges that come together and that we try to solve with Spell. The first is the infrastructure requirements for deep learning are really intensive. On the right, you see this chart. I believe this is OpenAI, who's publishes the state of the art in deep learning in each sort of domain of deep learning, either natural language or computer vision, et cetera, over time on a log scale with an estimate of how much compute it takes to train that model. And you can see not only is, even on a log scale, that a line that's going up and to the right, but even in this modern era, since about 2012, when GPUs and deep neural networks became the sort of go-to techniques in a lot of these domains, you see an even faster acceleration in the compute required to train one of these models. And I think when we think about making AI more accessible, not only is it access to compute, one of the barriers to entry, but also the tools that allow you to make large-scale use of that compute. Being able to run large-scale hyperparameter search, for instance, all of these are barriers to anyone getting into AI and to seeing more AI and deep learning in more of the products that we use every day. And the second challenge is that MLOps inherently, deep learning or otherwise, inherently has this looping feedback loop sort of workflow. In traditional software, you generally build, test, and deploy, and pretty much all software works, in that linear fashion. But machine learning is different. It's empirical, and so you often have cases where there's information that you're only going to learn later in a pipeline for a model that you need to use to go back and recreate parts of the parts of the workflow. So this inherent sort of looping nature of MLOps means you need all of the tools in one place, and you need to efficiently track every step of the workflow, something we call model lineage, so that you can go back and iterate on those pieces. And so, tracking that model lineage and putting everything on one standardized platform is a huge benefit when working on machine learning applications. And that's kind of what we are. There are two sort of main things we build towards. One is being end-to-end. So we take everything from the first experiment, the code and data that created a model, all the way through hyperparameter search, building a registry of models, deploying them, monitoring them, and then all the way back to iterating on those models and updating them on new data. The other thing that we do is we run on top of any hardware. So we support all of the major clouds, as well as on-prem clusters based on Kubernetes Slurm, or we have a private machines feature where you can register just a GPU machine under your desk that you'd like to target with Spell experiments. So a lot of flexibility in hardware, and a couple anecdotes. During my, on average, the GPU cluster that we ran on Facebook, the demand on it, the amount of jobs that were run tripled every 6 months. So it's an unbelievable acceleration you can see when you start getting into AI in the compute requirements and the costs associated with it. So we think that the flexibility to use different hardware and the sort of control that you have over the infrastructure that you're using is incredibly important when companies are looking to build and deploy an ML stack. I'm going to do a full demo, so you'll see a lot of this in action, but I wanted to talk about just two core concepts that really are incredibly important to how we build Spell. One is the idea of remote execution. So there are a lot of different ways that you might identify some code that you want to run on top of some data. You might need that to run in a specific environment, in a container that has different software installed. Creating an experiment, specifying it, and having it run is really an inherent part of doing things with ML. And our philosophy is that we want to give people the simplest on-ramp to that kind of workflow as possible. So we built this tool, a command line tool called Spell. And literally when you type Spell run in front of any command that you would have run locally, something that anybody that's a software developer is doing multiple times a day, we package everything about that execution, move it onto the hardware that you've set up as your Spell cluster, and run it seamlessly as a cloud running experiment. So there's a lot of infrastructure that goes into that. I'll show it later. But the core concept here is that our base primitive for running experiments in machine learning is remote executing them. Running them just like you would a Python script locally, but having that execute on a different piece of hardware. And what we get from that, even though this is just the same feeling from the perspective of somebody doing the work as running a piece of code locally, behind the scenes, we're actually turning that execution into a very precise and reproducible experiment. So we're keeping exact track of the commit hash of the code that you're using. We build custom environments, and we know everything that goes into the software environment that's required to run that code. We keep track of any data that you use, whether it's mounted in S3 or it's the outputs of another run. We know exactly what data was included, and we know the hardware. And that kind of forms this API. If you tell us, I want to run this code in this environment with this data mounted in this place on this hardware, Spell is really a machine for taking that and telling you exactly what the result will be. Before I get into a demo, just a quick list of features that we support. Cloud Jupyter notebooks, shareable, collaborative, and packaged with the environment and data that they need to be to run. We integrate with Git, so we track exactly what code you're running on Spell over time. We enable you to use spot instances, which can save 80% of your costs if you're using the cloud. Very appealing for the expensive AI and ML workflows. You can use your cloud credits. So if you're a startup just getting started and you have a lot of credits on any of the 3 major clouds, we can plug Spell into that, and those will be the things that you use on top of our platform. We do support distributed training. We have a great hyperparameter optimizer that automatically runs all the experiments. We have a pretty slick weights and biases integration where you can just type in an API key and everything that you run will show up in both interfaces. Once you get to deployment, you can package anything that was trained on Spell into our model registry and have different versions of models that you've trained. We'll automatically deploy that to Kubernetes, set up auto scaling, authentication, everything that you need. We also provide custom handlers. So, we're not just taking a model and turning it into an API as it's designed. You can write your own custom handler code that will that we execute every time your API is invoked. We support batching on GPUs, something that's incredibly important to actually getting performance in production out of GPUs. We have a whole automation system where you can go, take anything that you can do on Spell, write a quick Python script, and have it run as a multi-stage workflow. We integrate with CI/CD providers like GitHub Actions, et cetera. And with your serving cluster, you also get a Grafana dashboard, so you have lots of visibility into how the hardware and software are working together. That's kind of a quick rundown, and I want to jump right into a live demo. Let me just check how many. Apologies for this sort of infinite recursive desktop that you're seeing here, but just checking on our people that we have. Okay, so this is the Spell web UI. I'm actually going to start in the command line and do a quick example of running an experiment on Spell. So I'm going to go into some code. This is the PyTorch examples repository. This is actually, I just updated from GitHub. This is the most recent code directly off GitHub. I haven't changed it in any way. I haven't done anything I haven't done anything to it to make it run on Spell. It really is just code that I found in the wild. And so usually if I wanted to run this example, this is the word language model. So this is very similar to a GPT-3 type of model, something that understands the sort of structure of language. If I wanted to run this locally, I would run this main script right here, very straightforward. But I don't want to run this locally. I know that this is a very computationally expensive model to train, and I want to run it as an experiment on Spell. So literally all I do is type spell run in front of that same command. And I get a lot of different options on the command line for telling Spell how I want this to be run. I can do things like control the environment, add packages. I can select different hardware. There's a long list of features here, but I'm just going to use the -t flag, which is for picking a machine type. And I'm going to request one of type T4. So this is going to have a GPU attached that I know is going to make this run a lot faster. So once I start that, Spell is going to synchronize the exact state of the code that I'm working on. We're going to build a container that includes the code and any environment, any software packages that I need in the environment. We're going to find a machine type of type T4. We're going to start the process, set up all of our logging, and start the process running. As you can see, on average, this only takes about 5 or 6 seconds of overhead. And immediately I'm getting the same console logs. This kind of feels to me like something that I'm running locally, but it isn't. This is running, in this case, on our cluster in AWS. I can control C out of that. And even though I'm no longer tailing the logs, this is already running on our shared cluster. So here, this is the experiment that I ran. I have full control, so I can kill this, I can stop it. And because we have all the ingredients, if I click this button, I can rerun an exact copy of this code on a different piece of hardware or just as a duplicate of this experiment. I get sort of all of the sort of generic details of the run up here. Our metric system is collecting metrics from the ML frameworks. So here from PyTorch, I'm getting each epoch as it completes. I'm getting the batch number as that streams in. Live updating, I'm getting a calculation of how many milliseconds it's taking per batch, the loss, perplexity, et cetera. We also have live streaming hardware metrics, so CPU usage, memory usage, network activity, GPU utilization, disk usage, et cetera. Down here, I get, on the web, I get a live stream of the logs as they come out of this experiment. And then here, anything that's written to the file system during the run, we treat as one of the outputs of this experiment. So here, I know this model is serializing a different version of itself every time it completes an epoch, and I can see those files being created here in real time. After this is, yeah.
Hey, apologies to interrupt you. Would you mind zooming in a little bit on your screen? I think it's kind of tough for some of the viewers to see. Thank you.
My apologies. Yes, let's get a nice healthy zoom on there. Is that better, Sydney?
Much better, thank you.
Yes, and same with this terminal. We'll get that as big as possible. My apologies if that was tough to follow. So as I was saying, we snapshot the state of the container before we start an experiment, and we collect as artifacts of that experiment anything written to the file system during the run. So here we have this model that has come out of this experiment, and it will get saved back to our shared file system. This is shared across an entire team, organized by the experiment that created it. So in this case, you can see in this runs folder, I have all of the outputs of all the experiments organized by experiment ID, stored back to the cloud. What's nice about this is, it's much more organized. A lot of times you have, if you run 100 copies with different hyperparameters of the same experiment, you're often going to have thousands of files with the name model.pt. It's very difficult to keep track of what files are the outputs of what experiments. And so Spell automatically organizes that for you and automatically preserves the lineage from this file was created by this experiment, which is this code run on this data. The other thing that's nice about it is, since all of the computation and all of the data that we're using as inputs and all of the models that we have as outputs are going back into, in this case, S3, but this can be backed by any of the cloud storage systems or by private storage. Because you have everything in one place, you're never copying data between experiments. You're never waiting for, you're never really managing the data side of things. That's all sort of handled automatically under the hood by the Spell file system. So that's kind of basic experimentation and how you get something into Spell. And this might be early in the workflow where you're training a new model, you're trying to find something that you think works well on some data. Once there are a bunch of advanced tools on the experimentation side that layer on top of this. First, we have the ability to group experiments into projects. So here, when I'm grouping all of these runs of the same thing into a project, other people, this is a point of collaboration. So everyone that's working on this project can put their experiments in the same place. You can pick a metric to show over longer periods overall performance on that metric across the different experiments. And then you're also able to pick individual ones of these and compare them with an experiment and create more custom views, different charts of performance, et cetera. We also, from going from one experiment, oftentimes what you want to do is go from one experiment to a larger scale hyperparameter search where you're running hundreds of the same experiment and looking for the model with the best performance. So one thing, when you have Spell's infrastructure automation, we make this really easy. So in this case, we have this CFAR10 model that we've trained, but instead of using the run command, I use the spell hyper command. And what that allows me to do is insert tokens on the command line or in my code for places where I'd like hyperparameters to appear. And then Spell will prompt me for each of these hyperparameters for ranges that I want to search over, distributions. It'll ask me for a strategy, how many runs I want to run, and then finally for a metric to optimize for. So it's pretty easy to sort of set up a hyperparameter search from one experiment and expand that into 100 at one time. And then Spell handles all the rest. So here, this is the 30-way hyperparameter search. We ran 3 experiments in parallel, and then every time an experiment completed, we took the final results, updated our priors, and suggested new experiments. All of that happened behind the scenes automatically, and each of those experiments that we ran is a fully tracked Spell run. So here, I can click into this exact experiment, and I can see this is coming from hyperparameter search 3, but these are the individual tokens that were passed in on the command line, and this is what the experiment ended up being, and I can see the metrics in real time. For the overall hyperparameter search, I can see a comparison across one metric, or I can look at validation loss, for instance, and I can see which experiments performed best. I also get a table of the outputs, so I can see that. Let's see if I want to look at, in this case, on final accuracy on the validation set, we can see experiment 16 was the top performing one. And then down on the bottom, I can visualize each of the different hyperparameters and the results individually. So here I can see the effect of the size of the second convolution layer, the kernel size, and things like that. So hyperparameter search, really efficient on top of the sort of infrastructure that we've built, and a very simple way to use the sort of power of hyperparameter search to go from one experiment to automatically figuring out the best performing version of that model. Another sort of more advanced feature is our workflow system. So we found that there's a real important part of the process of building something reliable and robust with machine learning that involves weaving together multi-stage pipelines. And the options on the market for doing this are usually more oriented around production. So Airflow or any of the sort of like DAG-based graphical heavyweight workflow automation tools, they end up being a lot more work than is necessary to build something that's more oriented around training and machine learning. So we built this workflow system based on simple Python scripts. So you can write a Python script that can do things like start an experiment, can start multiple experiments and block on them completing. You can monitor metrics, so you can block until a metric hits a certain threshold and then kill some experiments. You can take the outputs of one run and then use them as the inputs of the next run. All of that can be automated, versioned, and happen sequentially. And so these workflows, in our workflow system here, you can see the individual components. And again, these are specific spell runs that are fully tracked. And then the final sort of piece of all this is our workspaces feature. So a workspace is a combination of a Jupyter notebook and the environment and code and data that's in it. I actually see Trey has one open here, my co-founder. So I'm actually going to view it, see what he's doing in, oh no, looks like I can't. So let's go to one that isn't open. And I will run this Sonic Dreams test. And actually, I'm gonna run a different one. Let's run this stock prediction model here. Trying to find one that won't require a GPU. This is probably a good one. So just like runs only take a couple seconds to start up, our Jupyter system is also optimized, also lives on top of our optimized cluster infrastructure. So we'll automatically build the right version of the container that we need to run this notebook. We will spin it up, mount the data in the exact place that it needs to be, and then we'll get a Jupyter interface really quickly. While this is starting up, these are the sort of details. This is the repository that it's based on. It's starting from this commit hash, some details about who was the last to start it, and then mounting data from the shared repository into a Jupyter notebook is really easy. So here we have a couple different run outputs that we put into the notebook, which will appear automatically. And then we have access here to the files that are part of the notebook itself. So any notebooks, any sort of images that we rendered, that type of thing. All right, so Jupyter should be starting in a second. And here we go. Sort of very, not just instantaneous access to running Jupyter notebooks on top of any hardware, but also a cloud version of it. So not only can I set these up and run them from anywhere, but they also come already pre-baked with the exact environment that I was using and the data in the right place, so I can just do my work immediately. All right. I'm going to shut down that workspace. And I think maybe I'll pause there. Sydney, do we have any questions that we should answer?
It looks like we're good, but yeah, we can leave a second for people in the comments to ask some questions. We've had Trey in there helping give some answers along the way. One of the questions was, do we support smart hyperparameter search?
Oh, yeah. Yeah, looks like Trey answered that in the chat. And I see we have some polls running. Really be interested in the results of those. Okay, so let me, in that case, I'll jump back in and we'll start talking about deployment.
And Serkan, would you mind making your Spell UI screen full screen rather than zooming in if possible, like full screen in the window? Yeah, thank you.
So I've used a Jupyter notebook to do some experimentation, or I've trained a model on Spell. I've run a hyperparameter search. I have a model that I think is performing really well. Let's go to this example, this CFAR10 search that we've run. Looks like by performance, it looks like this model 16 run 16 performed the best. So I can click into here, and I can look for the outputs of this run, because I know it would have written its model at the end. It's like this: use Keras, and we'll find the exact copy of this model. So once I have a model that I like here, for instance, in this Save Models folder, I can click this button, click Create, and I can identify this file and these outputs of a run as a new version of a model. Here I can give it a name. I can give it different versions. These are optional, and by default they'll automatically increment. But you can do things like write in tags like production or test, etc. And then I can create some metadata and make sure I leave some notes for people. So this model, once created, will go into our model registry. Here is where you can have multiple versions of different models created by different people, all in one place. And it's a good junction point between the sort of R&D process and, if you have different people that might be involved in model creation, maybe data scientists or AI researchers, and you have a different set of folks that are involved in production, this is kind of the junction point where they can communicate. So we'll go into the most recent version of this model. We can see who created it, we can see the resources, and we can see a link back to the original example that created it, and a link to the repository that was used when this model was created. So again, not just some files that are tagged as a model, but full sort of context and lineage back to the code and data that were combined to create them. So once I have this model in the registry, I then can turn it into a server. And I'll use this server as an example. So when I want to create a server, I take a model that's in the registry, I pair it with a handler that I write, and I pair it with a spec about the container environment that I'd like it to run in. So in this case, I've used, this model uses our default Spell environment, but adds a couple of pip packages. You can do this. You can customize it with app or conda packages as well, or you can provide a link to a container of your own. So we support sort of any environment. Once you have a model paired with a handler and a container environment that you'd like, Spell will automatically combine those ingredients, launch the model server, turn it into an auto-scaling endpoint in a Kubernetes cluster that we manage on our end. So there are a lot of different options for controlling how auto-scaling works. You can tie it to request latency, request volume. You can specify that each pod needs a certain amount of CPU load, so that'll auto-scale. We support auto-scaling on GPUs, and as I mentioned, we support batching on GPUs, which allows you to automatically send batches and get more usage out of GPUs as they run. Once a model's up and running, you get these sort of basic metrics here: request volume, failures, request rate, latency, 90th percentile latency, etc. You also get hardware metrics specific to the pods, so you can monitor each of the pods differently, individually, and you get pod logs down here. If you want to do more, for more advanced, a more advanced look into the serving cluster, you also get a fully featured Grafana dashboard deployed on top of it. So I'll go to the home dashboard here, and we can see even more detail on each pod and the hardware metrics around those. So Grafana is a really nice feature. And the final thing is that the same system that collects metrics here, the same system that's giving us total requests, failed requests, et cetera, is the system that we use for experiments. So you can define custom metrics here. You can log anything out of your production models that you need. You can also, once you have those things logged, it's very easy to pull time series and compare time series that you're getting from production and metrics from production to metrics that you saw in that experiment in training. So I think one of the most important things that we can do in machine learning is make sure that the sort of things that we saw in training, not just on the training set and the validation set, but those metrics also compare well to what we're seeing on live traffic and with live data. That is kind of the that's kind of the end piece of the workflow. So going all the way to a model in production. We built a little demo of a sort of end-to-end model here that I'm going to show. So this is a generative network that we trained on a whole bunch of paintings by the American painter Bob Ross. And so on the left here, what I can do is I can draw a little segmentation map of where I would like some things to go. So I'm going to paint a tree here. I might put a mountain in the background, and I'll fill that in. And maybe we'll put a river sort of flowing in the background here. Please excuse my lack of artistry skills. But what this is going to do is send that segmentation map to a generative network that is going to try to fill in those pixels and make it resemble as best it can a real Bob Ross painting. So not bad, not bad. I think I'm the limiting factor here and not the model. But what's fun about this is it shows kind of a cool example of what can be done with AI and ML, but also this is using our model serving infrastructure. So if I go back to this Grafana dashboard, we'll see the increase in utilization that came from executing that model. Let's see, I think you can see it here, but you'll see an uptick in compute resources there. And then if I go back to the serving dashboard, you can see that we had a couple, we got some extra requests, and you can see the request rate going up, latency, et cetera. And then again, if I'm curious about that model, if I'm not happy with the painting that it generated, I can click back to the model that created it, and I get a full record of exactly how it was created. I can click back to that run. And if I want to, I can regenerate that model, changing some of the individual parameters. So that's deployment on Spell. There are a lot of features that I didn't get into, very sort of things that are important for a production workflow. Things like we allow for asynchronous handler. So if you want to do something in the main body of your handler, but then you also need to log some data, sample some production data, you want to do something outside of the main body of the request, we support that. Our auto scaling system is pretty robust. We have a number of customers who are literally hitting spell models directly from customer-facing apps or websites. So there's a lot that goes into our serving system that makes it appropriate for using in a real production environment.
Hey, Serkan, we had a question in the chat if you have time to dive into it. They were curious to learn
Sure.
more about distributed training.
Yes.
Gave some info about that, but I thought it could be helpful to show it off a bit.
Absolutely. So I don't have a demo prepared, so I'll have to talk through it a little bit, or maybe we have an example in here. We have two sort of methods that we support for distributed training. The first is if you use a library called Horovod. We find that that's the most popular framework for doing distributed training. And I'm actually going to pull up the command line. If your code does support Horovod, then doing a distributed run is actually really simple. With on the run command, there's a -- distributed flag that you can use, and this will use n machines of whatever type you've specified and automatically run a copy of the model on each individual GPU in that machine. So if you want to run a 16-way hyperparameter 16-way distributed run across 4 machines that each have 4 GPUs, you would do -- distributed 4, and you would select a 4 GPU machine. We would automatically run that using Horovod. There are more complicated ways of doing distributed training. There are some frameworks where you run your own parameter server, you have multiple worker nodes. There are more complicated ways of doing it that we support, but they do involve more customization and using the Workflows API to get running. Hope that answers the question. I should mention, so under the hood, what Spell does is we identify the machines that you need. We set up MPI between them, which is the sort of infrastructure that they're going to use to communicate gradients and parameters back and forth, and then we execute your run on top of that. So we do all the infrastructure setup, and if you're using Horovod, we set it up so you can just use the -- distributed flag in real time. While I'm in here, I guess there are some other features I might as well highlight. One is the ability, if you want to use your own custom Docker image, you can pass in a Docker Hub tag. You can pass in a link to another container repository. You can use any Docker image that you want for experimentation. We have this feature where we'll automatically gather dependencies from the current environment. So if you don't feel like typing out a pip file or anything like that, we'll just gather everything, kind of like virtual env, and recreate your environment precisely on your in your experiment. Or you can provide pip packages on the command line, or you can provide us a requirements file. Same for Conda, same for apt. We also support TensorBoard. So not only can you we automatically collect TensorBoard and metrics if you turn it on and give you the TensorBoard UI. We'll also, anything that you log to TensorBoard will also appear in our metrics UI, so you can pull that via the API. You can see them stream in real time in our interface. They'll be stored in perpetuity, et cetera. You can add different labels to runs programmatically or in the web UI, so that's easy for keeping, if you have thousands, tens of thousands, hundreds of thousands of experiments, you can keep them organized in that way. This is a really great feature if you are running on top of Spot instances. Machine types can be created that are Spot, or they can be created with on-demand instances. When you're using Spot instances, we can also auto-resume your jobs if your Spot instance gets interrupted. So when you're using a Spot instance, if you're just using the sort of like raw instance, you don't have a lot of guarantees about how long your job is going to run. And if you're not proactive, all of your work will be lost when that instance is shut down. What Spell automatically does for all Spot instance training is we detect that your instance is going to be shut down, and we automatically save all of the outputs of your run back to the cloud, so you don't lose your work. And if you have auto resume turned on, what we'll do is we'll remount all of those outputs, we'll reassemble the code, we'll put your experiment back together and automatically resume it on another spot instance without you having to do that manually. So really great infrastructure for getting more reliability, more sort of efficiency on top of spot instances, which are often 80 or 90% cheaper than on-demand instances. We support auto stopping. We also support saving sort of all the stuff that you're typing on the command line to a file, so you can just read from that. And a lot of documentation, and I think that basically covers it for the command line. So good question about distributed training. Thank you for that one.
Yeah, we also have another question about monitoring, particularly for computer vision, but worthwhile maybe mentioning Arise again.
Yeah, so one thing that we find is that because we have, I would say, two features of Spell. Let me get back to my other window here. There are two features of Spell that make it plug into basically any monitoring infrastructure really well. And there are companies out there, Arise, Fiddler. There's a whole industry of like great explainability, sort of drift monitoring, those types of model monitoring tools. So in our model servers, not only we have this feature of asynchronous execution. So usually what we'll do, usually these products involve sending some of your data or sampling some of your data via an API that they provide. So what we usually do is hit that API with sort of either with inputs and outputs from the model, and optionally, if we can look up ground truth for some of those things, we can send those as well. And we do that in the asynchronous body of the handler, so it's not interrupting the efficiency of the code. And then also because we're tracking the entire lineage, it's very easy to programmatically go from a model all the way back to the original data set and then upload that as well as part of the ground truth for a model. So I don't think we have a demo with any of those integrations shown up, but because we handle all the infrastructure, plugging into other model monitoring infrastructure is really easy, and they do a really great job of automatically showing you drift and the basic things that you want to know about your model in real time. Great. Let me stop sharing my screen and jump back into the chat.
Yeah, Tomer just asked, where do we store the model performance metrics?
So we use Kafka. So between logs, metrics, particularly if you're doing huge hyperparameter searches, the volume of data coming out of experiments can be huge. So we have some rate limiting infrastructure on the individual machines. They all go through a Kafka pipeline. They're stored sort of temporarily in Kafka and then written ultimately to S3. So very robust infrastructure that we've built to make sure that we can capture all of these metrics from large scale experiments. All right, let me go back. Let me see if I can. There it is. Okay. All right, looks like we have a lot of people in the chat. Looks like Trey has been jumping in and answering some of the questions in the chat. Thank you, Trey. Got it. Yeah, some questions about sharing GPUs in production. Pretty cutting edge stuff, especially given the memory limitations of models. But definitely something that is interesting, and we hope Kubernetes will support natively. Is that I guess Trey is just in the chat. I don't know if we have any customers who run multiple models on the same GPU. I would think that would be theoretically possible. Let's check into the polls. like we don't have a ton of results yet. Let me jump back in. So a couple highlights. The healthcare space has been really sort of not just interesting for us in terms of customers, but also just fascinating in terms of how AI and ML are getting used on new treatments. So a lot of our customers are in the healthcare space. They use us for doing large-scale experimentation, things like genomics or using machine learning on genomics, medical imagery, or a lot of our customers are doing multimodal learning. So combining text that you might have from medical records or from clinical trials with imaging and other sort of high dimensional data from the trials themselves, and using that to sort of either develop new treatments or sort of get better understanding of existing treatments and how they're working. We have one of our customers will be publishing a paper in Nature about early detection of Alzheimer's at some point this year, and all of that work and all of that research was done on top of Spell. So really exciting stuff in healthcare. I would say the second biggest category is just NLP kind of everywhere. We have some media companies. We have a dating site that that's really interesting. Anytime that you have a lot of customer text and you want to do some nuanced sort of contextual thing, building NLP models has been really popular, both in training and deployment, because we support both. Let's see, other interesting use cases that come to mind. Chatbots, so another NLP. There's a team at a major financial institution that trains chatbots on Spell and deploys them for customer service. Great. Let me jump into deployment. And actually, for variety, I'm going to start with the demo that we have.
And while you're bringing up this demo, if people in the chat could share, we're curious to know, what does your MLOps process look like now? Are you using infrastructure that you've built in-house? Are you using open source, using tools like Spell? We'd love to have an idea of kind of what your flow looks like right now.
Yeah, that's a great question. I would love to hear what people are using now, and what kind of the most painful point of their workflow is at the moment. So this is a fun demo we built to sort of showcase Spell and our deployment capabilities. We trained a generative network to identify sort of different objects in paintings. In this case, we trained it on Bob Ross paintings. And once it's identified those things, you can create on the left here a little segmentation map of where you'd like different objects to go. In this case, I'm going to draw some happy trees. And let's see if we can make these a little more realistic looking. Yeah. And so I'll draw some trees. I'm also going to put a mountain in the distance. Let's say like just a little one kind of coming in here. And then I would like you know what, I think we'll do this by the ocean. So let's make it, let's see if we can put some ocean over here on the left side of the screen. And so when I click run here, this is going to take this image, send it to one of our model servers that's serving this generative model that will look at where I've identified things and try to fill in those pixels as best it can, and try to recreate the look and feel of a real Bob Ross painting. So let's see what this comes up with. All right, not too bad. So we can see we have the ocean here. The trees came out pretty good, I think, and then a mountain in the distance. So kind of a fun demo, but really, all of this is running on top of our model serving infrastructure. So going back to the UI, I'll kind of work through how I can deploy a model once it's trained, and then we'll see this model specifically. As we can see here, this is my experiment. I'm training this language model. It's still running. It's on Epoch 16, and as before, it's constantly serializing a copy of the model to the file system. So we're tracking that. If this is, I might take this and move it into a hyperparameter search and try to get the absolute best performance before I do this. But let's say I just wanted to deploy this. I would click this Create Model button. And I can take that model and any other files, so I can attach other assets. There might be other things that I want to package together, but that collection of files will get added to the registry as a model. I can give it a name. I can version it. This can either be auto-incrementing numbers, which is the default, or you can add tags like, production, test, that type of thing. And then you can add some notes as metadata for it. And that will go directly into our model versioning system. So in this case, that Paint with ML model, that's version 1, and that's sitting here. Now, because, again, the model lineage is really important, knowing exactly how something was created. So here, even though this model, this is version 1 of this model, because it was created from the outputs of run 10.11, we have that context. We can click back into the exact run if we want to, and we could recreate that model from scratch. So once I have a model in the registry, I can go into our serving infrastructure, and I take that model and I pair it with a handler that will have access to it. So here you just implement a basic handler function that will get fed inputs from the API. You run them through your model and can decide on the outputs. And then I also pair it with a container. In this case, I've used just the spell default container, probably the same one that this was trained on, but I've added some pip requirements to it. So we'll build something that includes these pip packages. You can also add apt packages if you need stuff built into the OS, or we also support conda files. You also can provide your own container, and that can be a GitHub tag, it can be in a private container registry that you've registered, any of those different things. And once I pair those things together, we will deploy them as a URL, an API endpoint here automatically, and we'll turn on auto scaling. In this case, you have a bunch of different options for how you can set up the auto scaling. You can have it auto scale by CPU utilization, by request rate, GPU utilization, request per second, that type of thing. As I mentioned, we also support auto batching on GPUs, so this is a huge performance win when running models through big beefy compute like GPUs. Here, it looks like some people have been trying the model. That's great. Here you get, you can see basic metrics like total requests, any failures that happened, requests per minute, median latency, 90th percentile, etc. This is the same metric system that we use in experimentation, so it's very flexible. Not only do you get these default metrics that are coming out of the API itself, but you can log any custom metrics that you want. They can be images, they can be text. The metric system is designed to capture all of the things that you might want to know about a model, either while it's being trained or in production. You also get hardware metrics per pod, so you can see the CPU utilization and how many cores are active, memory usage, etc. And you get logs for individual pods if you need to debug things. This is one way. For a sort of another way of looking at the hardware underneath this is our Grafana dashboard. We automatically deploy this as part of the serving cluster when you sign up for Spell. So this is something you can click into and get even more detailed look into how your hardware is being used and how the cluster is performing. The sort of final thing that I want to show is I'll run this one more time and just showing how that request shows up in the metric system alongside the model server. Let's see, what do we want to do here? Let's add a rock over here. That looks like a rock. And then maybe some plants. All right, so we're going to get another version of our slightly more interesting Bob Ross painting. Okay, so we get some plants growing and a little rock in the corner. We can see that request coming into this model server. We can see it in the Grafana dashboard. We'll see a little spike in CPU utilization. Let's see if that shows up. This might be delayed by a couple seconds, so we won't wait for that. But then I can click from that model into the exact version of the model. And I can click from this model registry back to the original experiment that created it. So not only do we have a model running in production, we're monitoring it, it's auto-scaling, we know everything about it, we have a lot of flexibility and production readiness in the infrastructure around it, but we also have a precise record of exactly how it was created, all the way back to the commit hash of the code and the versions of the data that went into generating it. Just to wrap up after the demo, this is something you can try yourself. Deploying a spell cluster takes about 5 minutes. We support all of the major clouds. All the instructions are super clear. If you want to try a cluster, it's free. And here's the URL that'll walk you through it. Very easy to get started, and you can do all the things that I was just showing immediately. And also, we're hiring. So if you're interested in charting a course for the tools that make AI and ML a reality for teams and a real part of the products that we use every day, that's what we're doing, and we'd love to hear from you. So check out our careers page on our website at spell.ml.
Great, thank you, Serkan. Thank you everyone for joining us today. Yeah, if you have any questions, you can still throw in the chat and visit spell.ml.
All right. Thanks, everyone.